So welcome. Let's go on to rotation notes. Reason why we did center of mass is because things rotate about their center of mass. What we're going to do on this is we're going to look at some physics that we've done already from a rotation point of view. So we're going to look at things like angular displacement rather than linear displacement. We're going to look at angular velocity rather than linear velocity, and angular acceleration rather than linear acceleration. We're going to look at how we convert between angular parameters or quantities and translational parameters or quantities. And that's going to lead us eventually onto torque, which is we're going to touch on. We're going to go back to, we're going to continue with it in the chapter after this. We're just going to introduce ourselves to it. And then we're going to look at things like moment of inertia and rotational energy. And then finally, rolling motion. My basic philosophy is that whatever you've done in linear, transverse physics, you can do in rotational or angular physics. You can use either term. So you learned that delta x equals x final minus x initial. Well, you're going to learn today that delta theta equals theta final minus theta initial. And you learned that Vf equals Vi plus A delta t. And you're going to learn that omega F equals omega I plus alpha delta t. And you learn that kinetic energy, UK or KE or K, whatever you want to call it, is a half times m times v squared. And you're going to learn that UK rotation is equal to half I omega squared. Now, what might be driving you crazy is all these Greek letters. Some of them you're kind of used to. You know theta. I don't think that drives people crazy. And you probably kind of, oh, alpha, you don't see it that often. But then this little omega thing, I mean, what the heck's that about? And only thing I can say to you is that we've run out of letters so many times that we can't possibly be using. If we use A for acceleration transverse and A for acceleration angular, then we can't have an equation that talks about going from one to the other. So we've got to have some difference. So somebody decided to use Greek letters, and so that's the way it goes. And it's not, the math is no harder, it's just the symbology is uncomfortable. I put a little video on there. I think it used to be on there, but I'll double check. I put a little video on there of this one person pronouncing and naming all the Greek letters. And there's little, I mean, I'm sure if you just Google it, there's handouts, Don't be in a situation where you don't know the common Greek letters. So what does that mean? What I mean is when a Greek letter gets mentioned in class, learn it. Don't stand away from it. Learn it. Just embrace it. It's just a letter. It's just like Z or F or G. It's just another letter. But you don't want to be stumbling over that letter and that when you're trying to do a problem going, what is that thing? You want to know how to say it. You kind of know what it stands for, etc. And I think the best way of doing this entire next section is you do conversions. So I know that X is like theta and V is like omega, and I know A is like alpha. And then I know, for example, that F is going to be like torque, tau. I know M is like I. I know that K, E, trans is like K, E, rot. I've missed some out. Oh, yeah. I know P is like L. So I can look at one side and go, oh, yeah, I know that already. So if you're comfortable with doing these kinematics before, great, you're going to get them again. If you weren't, then, you're going to get them again. So it doesn't go away. Apologies for this. I meant to look at it, but for some reason, when I do the conversion, I didn't type it like this. When I do the conversion, sometimes I don't know whether it's to the PDF or whether it's to the PowerPoint or whatever, but it loses the terminology. Consider point P moving in a circle around. So we have this point P, and it's moving around the circumference of a circle. So when we look at it, point P's over here. How far has it moved? It's moved so many meters around the arc, and we call this the arc length. I think it's ARC length. And then we have the radius R. And what we say is, oh, if you look at this, we can define an angle. Theta is defined as the arc length over the radius. It's how far you run around the circle compared with the radius of the circle. And I can tell you now that when space aliens come, if they do come, they'll know about this. They won't have a clue about the degree, but they'll know about this. So this is not made up by people. This is not arbitrary. It comes out of something very fundamental. And it's a ratio of how far you go around a circle to the radius of the circle. It's fundamental. And therefore, it's bedrock. It's the simplest way of representing angles. It's the most natural way of representing angles. The reason why we don't tend to do it much is because two reasons, I'd say. One is that 1 radian, so this is in radians, not degrees. So 1 radian is a massive angle. If you went to a shop and say, I want a radian of cake, that cake would only get divided up into 6 bits, roughly. And we tend to have more people want cake. So, you know. And then the other problem with it is that 1 circle is not a whole number of radians. There's not an integer number of radians in a circle, and it's a pain, you know. And we don't like that. It kind of feels raggedy. Why is there not a whole number of radians in a circle? It just seems like it's just the way it is. And historically, you know, back in the day, in the basically northern Syria and eastern Turkey and that whole Fertile Crescent, 3,000 years ago, probably 3,000 years ago, they had a hexadecimal system, a basic system, and that's why we have, you know, 360 degrees and, you know, 24 hours in the day and all this kind of stuff. That's where all that comes from. Okay. So just get used to it. Don't let this put you off. Now, from now on, you have a choice. You can name your angles in degrees or name your angles in radians. And if you have the right number in front of the symbol, the answer's right. Numerically, the number of degrees is not equal to the number of radians, so you can't just have any unit you like. They're different units or different numerical values. But if I say, what's this angle? And you say to me, it's 2 radians, and it is like, let's say, 125 degrees. I don't know if that's exactly right, but they're both equivalent. So you're right, of course you're right. Yeah, it is 2 radians. It's also 125 degrees, whatever it is. So you have a choice. Equations, they expect one or the other. If you're dealing with anything that has an omega in it or an alpha in it or anything like that, best bet, unless there's a good reason not to, you're doing a conversion or something, if you can't decide and there's an omega in the equation, put your angle in radians. That's the best bet. This comes up again in Physics 2. We kind of use this, all of this mathematics actually we use again in Physics 2 for light and waves and electricity and magnetism. So all this circular stuff, all this rotation stuff is really important building blocks. Angular displacement. Well, my angular displacement, it's not a position, it's a change of position. So that would be theta final minus theta initial. Just like, you know, delta x equals x final minus x initial. So same equation, really. And angular speed, this is omega, is equal to limit as delta t goes to 0 of... it's going to be d theta by dt, which equals d2 theta by, which equals delta theta by delta t, which is d theta by dt. And that's just like we said before, that v is equal to dx by dt. Remember that? And then if we want angular acceleration, which is alpha, that is the limit as delta omega over delta t, which equals d omega by dt, which equals, of course, d2 theta by dt squared. And this is like saying A is equal to dv by dt, which equals d2x by dt squared. I learned all that stuff. I'm not learning it again with different symbols. I'm just going to learn the conversion of the symbols. Yeah, it's like, this is the same physics. Every point I rotate. Now, so, all right. When I was a student, I would have said, but I know how to do the translational stuff. Why am I learning this stuff? This is just a total waste of time. I can do the translational stuff. If you give me a circular motion stuff, I'll just do it translationally, And the problem is, so nothing gets into the textbook and stays in the textbook without it being really useful. It's like your tools in your toolbox are there because each one does its own job and you want to use them. So if this is in the textbook, it's because it makes you more powerful. You can probably do it, you can do everything from first principles if you're prepared to invent and create and be amazing. But if you learn stuff, it just gets a bit easier. And what they're saying here is if you just learn this symbology, everything's a bit easier. And here's I think the key thing. If I have a race car track, let's say that I have, well, actually this happened when I was in high school. We had sports day, and they had us run around a track. And I was on the outside track, so we all started off, and I was on the outside track, so I had to run further than the people on the inside track, and so the tendency was to cut the corner, ignoring the fact that I started about, 300 yards in front of them because, the people who designed the track knew that on the outside track you'd go around a bigger thing. So I started cutting the corner. People behind me started telling me to get out, and all that kind of stuff. So if you tried to do a circular problem translationally, is the problem with it. If you try and do a circular problem translationally, and you want everything to keep up, then for me to keep up, this particle has to go that distance in the same amount of time that runner goes that distance, in the same amount of time that runner goes that distance. So you could say that each of those runners has a different speed because they're going at different rates. They've got a different, and if they speed up or slow down, they've got different accelerations to kind of get going, speed up, and stay the same, etc. But if I talk in terms of angular terms, then every point here goes through the same angle in the same time. So every point on this pattern has the same angular velocity, and if it's accelerating, the same angular acceleration as every other point. So whereas if you try and do things using translational stuff, you've got to have how far am I away from the middle, and then you've got to do some calculation to get what that is. If you're doing angular stuff, you just say, oh, I know the angular displacement, I know the angular position, I know the angular velocity, I know the angular acceleration. Every point is the same. That's a tremendous simplification of the problem. So every point on a rotating rigid object has the same angular displacement, angular speed, and angular acceleration. And that's just like such a time saving, being able to do that. So that's what makes this really useful. So in my head I have this x is like theta, and delta x is like delta theta, and v is like omega, and a is like, what's this letter? How do you say this letter? Alpha, yeah. So just as we said, Vf equals Vi plus A delta T, I'd say, what's that letter there? Omega, yeah. Omega F equals omega I plus alpha delta T. Delta T is the same. There's no angular time, as far as I'm aware anyway. Maybe Einstein has an angular time, but I don't, But, the other things, there is angular stuff. So you know these four equations. and they're in your deep memory because you kind of drove them into your deep memory, well, they're still there. Just do the conversions. If you learn these equations and they weren't in your deep memory, then put them in your deep memory because you're going to need them again for the next, for whichever test they come up in, which I think is test 3. Student runs 40 meters around a circular track. So here we have the student runs 40 meters. And it's a 50-meter radius track. What is angular displacement? So angular displacement, well, I'm going to change that. I'm going to say angular position, just to get us started. So I want to know, if this is 0 rad, how many rad is this? I want to know the position. And I say, well, okay, we said that the angle was defined as the arc length over the radius. So the angle is defined as 40 over 50, which equals 0.8. 0.8 what? Radians. Now, what are the dimensions of the radian? Think about your L and your T and your M. So what are the dimensions of the radian? It's a length over, which is meters over meters is what? Nothing. So it's a unit which is representing a dimensionless thing. So units are not exactly the same as dimensions. Sometimes you can have units with no dimensions. Same for a degree, by the way. Degree is dimensionless. Okay. So that wasn't so bad. Now, to answer this question at displacement, I'd say my displacement is equal to my final position minus my initial angular position, which is 0.8 minus 0.0, which is 0.8 radians. It's the same numerical answer. It's the same thing, but it's kind of saying something slightly different, yeah? My address is not the same as how far my address is from the starting point. Yeah? So, just a little bit of a fine point there. A point on a rigid cylinder has an angular velocity. Now, I do my angular velocities like curvy. Omega is equal to plus 3 radians per second. At time, t is equal to 2 seconds. And the cylinder has an angular acceleration. I feel a kinematics question coming on here, which equals minus 5 radians per second squared. And then what is the angular velocity, omega, when t is equal to 6 seconds? So let me ask you a question to begin with. Is this particle speeding up or slowing down at t equals 2 seconds? Why do you know it's slowing down? You're right. How do you know it's slowing down? Yeah, your velocity and your acceleration are in opposite directions. So even though you're on a circular bit, you can still use that same insight. Man, I haven't done this in a while, so I'm going to do my list to jog my memory. And I'm going to say omega I is equal to plus 3 radians per second, and then alpha is equal to minus 5 radians per second squared, and my delta t, of course, which equals t final minus t initial, which equals 6 minus 2, which equals 4 seconds. And then what else do I have? I use that up. Alpha, use that up. Use those two up. I want to find what my omega f is. And if that doesn't help, I'm going to say VI, A, delta T, VF. I get it. VF equals VI plus A delta T, which is the same as omega f is equal to omega I plus alpha delta t. And then I say, well, omega f is what I want. Omega f is equal to omega I plus 3 added to minus 5 times 4. 4 because it's the difference in time, and we started at 2 and we went to 6. So it's the difference in time. So omega f is equal to plus 3 added to minus 20. Omega f is equal to minus 17 radians per second. So the numerical answer is A. Minus 17 means that I'm going in the opposite direction. So I was going in a counterclockwise direction, but slowing down. And then I stopped. And then I started going in a clockwise direction, and that's where I am. That's that minus 17. It's a bit like, you know, it slows down, stops, and then so same science applies. Typically, we take counterclockwise rotations as positive and clockwise as negative. Just the way it works out. Okay. So not bad. Expect some kind of, if I've got time, expect some kind of kinematics question on that. It's like, you know, it's just change the symbols and you can do it. Now let's do translations. I know this one because that's my definition. Theta is equal to the arc length over the radius. So rearrange it, and I get the arc length is equal to my number of radians times my radius. I'd like to be able to do a conversion between translational. Let's say I'm running around a track, and you know I know my S and I know my R, so I can do this conversion and get the angular stuff. I'd like to be able to do the same thing where I have a V and what is my omega, you know. And if I'm speeding up, I'd like to have an A and what is my alpha. Not talking about centripetal acceleration here, talking about translational or tangential. It's translational because you're going forwards, and it's tangential because you're on the edge of a circle. That's why they call it tangential. So I'd like to be able to do these conversions, and I'm going to pull it out of a hat. I'm not going to prove it to you. I'm going to pull it out of a hat and simply say, oh, look, here's my linear bit. Here's my angular bit. And how do you spell angular? A-N-G-U-L, angle, A-N-G-L-E. A-N-G-U-L-A-R, yeah. And notice there's an R on the end of the angular, okay? So there's an R on the end of the angular bit, and there's an R on the end of the angular bit, and there's an R on the end of the angular bit. How do you spell linear? Oh man, it don't work, does it? Don't worry about that. I'll have to start calling the linear translational. There's no R on the end of translational, you know. But angular, just remember angular. It's easy to get these backwards. So just drive in angular, and you'll get them right. Now, this is interesting because we have AC equals V squared over R. We can substitute in for V squared, can't we? And we get omega squared R. And that's interesting. Here, the radius, it's an inverse relationship with radius, and here's a linear relationship with radius. And that's interesting. And it turns out AC has a linear relationship with radius. And the reason why you know this is because the omega is a fundamental thing, whereas the velocity is a combination of a displacement and a time. So it's interesting. So just know, you don't need to be able to justify it, just know those two. know the conversion. Well, you don't even need to know those two. Just know these conversions, and you already know that, so you can figure that one out. Point that is 5 meters from the turning axis. So this is 5 meters of a rigid cylinder. Has a angular velocity, do a little curvy arrow, of +3 radians per second. I did that the wrong way around, doesn't matter. I'll correct it. I like to have my, oh no, I didn't do it the wrong way around. Man, I'm sorry. Let's do that. I'm sorry. So, like that. So there's my omega. To begin with, put down your symbols a lot more than you would do later on, because you're just driving it in. And then what is the tangential speed? So here's the, I'm going to change colors just so that we don't get these two arrows confused. So here's my tangential speed, V tangential. And I say angular, I say my V tangential is equal to omega r. If you like, to begin with, I'm going to say S is equal to theta r. I'm going to say Vt is equal to omega r. I'm going to say At is equal to angular, alpha r. So I know that. So then I can say my Vt is equal to, it's just simply +3 times 5. Vt is equal to +15 meters per second. How did I stop myself from making that mistake? I looked at what I wrote down. I'm grading my physics 2 people. I got some people that were just, they're refusing to put down anything to the left of the equal sign. They're just putting down letters and numbers like phrases. And so they wouldn't catch that because they wouldn't have a VT in front saying, hey, it's the velocity. They just have a number. And so when their mind says the wrong thing, there's no visual to stop them and say, no, that makes sense. So please write in full sentences. A rigid cylinder spins about a turning axis that passes through its center. So there's my axis. We usually call our axis 0, don't know why, or O, I don't know why. A point is located 3 meters from the turning axis, so let's make that 3 meters. And tangential speed is 6 meters per second, so let's put this down as V tangential equals 6 meters per second. And then what is the tangential speed of a point that was located 4 meters from the turning axis? Let's change colored pens. So let's change the color of pens so I can see the difference. So that's 4. So I'm going to do it, doesn't matter which direction it's in, it's out here. That's 4 meters. Vt equals. Let's distinguish between these. Let's call this Vt4. Let's call this Vt3 so I don't get the two of them confused. I want an equation. The velocities are not the same and the radius are not the same, so I can't put those equal to each other. What is the same for all points on a rigid rotating cylinder? What was that? Angular stuff, isn't it? Angular stuff is the same. So I can say omega for 3 is equal to omega for 4. Because it's the same. Equals a constant, equals constant. Yeah. Now, angular, I know that Vt is equal to omega r. So I know omega is equal to Vt over r. Okay, so that means that Vt3 over r3 is equal to Vt4 over r4. Notice I'm just putting those subscripts in. I decided that. It's not the book. I decided that. It's the way of me helping understand what I'm doing. And you can do that. You can have ownership of your subscripts and you can put down little things in there that help you. It's, So then we turn around and say, okay, well, I know some of this stuff, don't I? VT3 is equal to 6 meters per second, and R3 is equal to 3 meters, of course. And VT4 is equal to, I don't know, meters per second, and R4 is equal to 4 meters. Oh, this is fine. VT3 is 6 over 3 is equal to VT4, which is what I want, over 4. Or VT4 is equal to 6 times 4 over 3, which equals 8 meters per second squared. Meters per second, not squared. Meters per second. And it's going to be a plus 8. Signs do matter. It's plus 8. So, all right, conceptually, you had to spot that it was the angular speed that was constant, sometimes called angular velocity, which, you know, is changing direction. So, but say angular speed. So the angular speed is constant, and that was the conceptual bit. And if you got that, if you didn't get that, then you were kind of flummoxed. But if you got that, you were on your way. And then I had to know that my translational is equal to my angular times r, and then do the substitutions. Mathematically not hard, just uncomfortable. It's uncomfortable. Yes?
Why is it meters per second squared?
It's not meters per second squared, no. I crossed it out.
Oh, sorry.
Yeah, I just didn't do a very good job of crossing it out. Yeah. In fact, I should erase it. Yeah, that's exactly right, and well done. Eraser. Yeah. Cool. So not bad. Okay. So what we had so far, we've had some kinematics, and then we had some things with rotation, with translation from one to the other. So second skill. Third skill. Yeah, okay. Is about torque. I need a volunteer. Will you be the volunteer? So I'm going to ask him to push this door open, but I want you to use one finger, and I want you to push it at the very edge. Okay? Now I want you to do the same thing, but I want you to push in the middle. And now I want you to do the same thing and push near the hinge. Don't break your finger there. Yeah, okay. So can you tell which was the hardest? Near the hinge, yeah? Thank you. Yeah. So same, I mean, you need, to get the same turning effect, you need a bigger force nearer the hinge. So the turning effect is not about just the force. It's about where the force is in relationship to the turning axis. And we call that a torque. Where would you find a torque, the word torque, been used in everyday life outside of physics class? Torque wrench. You know, if you go to a garage. These days you don't see a physical torque wrench very much. You get these like little pneumatic impactors, and you basically, and they dial in whatever torque they want, and they go zzz, zzz, zzz. And that in the end, that zzz is supposed to be the clutch saying, I'm at the torque that I want, so it turns it as tight as you want it, and then it just, the clutch releases and you don't get any tighter. How many people have changed their car tire and had to stand on the wrench to actually get the lug bolts off? Yeah? I mean, because people go, oh, I don't want to be sued for making it not tight enough. So they crank that torque up to quite a high level and then go zzz, 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 and it's your problem getting the thing off. They don't want to be sued for the thing not coming off. I understand that. It's like that. But I've had it where I've had to stand. I put the lug wrench in, and I've had to stand with 2 feet, my feet on the top of the car, just bouncing to try and get that thing to undo. But that's where you find it. When I was a student, there were 3 of us in the same coffee. So in Britain they have morning tea and afternoon coffee, morning coffee and afternoon tea. And there were 3 of us students in the same, there was a lot more, but there were 3 of us who were taking our driver's test on the same day. We'd all taken it multiple times before, because in Britain, the only person I know who passed their driver's test the first time was my sister-in-law. And she was 17, fearless, and she just kind of drives. When you get to like 20s, you kind of know it's kind of dangerous at times. And I don't know anybody who was above anybody other than her who got through the first time. It was my 3rd time. Mind you, the first time I did go down a one-way street the wrong way, but, you know. Didn't know the town, they'd take you out, didn't know the town. It was like, you know, traffic was backed up. I thought, oh, I'll just cut in this lane here. The guy goes, this is one way. No, this is not one way. So I was like, oh, God. So anyway, they were running bets on who would not make it through. You know, you could bet all of them get through, none of them get through. You know, this one gets through, you know, all these variety of bets. And we all got through. It was like, great. And then my 2 buddies immediately went and bought cars. And the very big guy bought this tiniest little car you'd ever seen. And the very, you know, the smaller guy like me bought this huge car. It was a bit like one of those cartoons, you know, like Pink Panther, where you get the police guy in the little police car and all that. It's kind of comical. And they hated their cars. So they decided to swap. Both cars were pieces of junk, and they decided to swap. Just swap. So they just swapped the cars. And then within 2 weeks, one of them had a really good car, and the other one had a really horrible car. And whenever you do that, you should never sell anything to people you know, because it always comes back to bite you, because, you know, as soon as you give them the lawnmower, it falls apart, and they feel resentful, you know. And there was a lot of resentment going on. And the guy who had the really good car said, well, all he has to do is fix it. And I said, what did you do? And he goes, I got myself a torque wrench. And what I did was I went around the cylinder block and just slackened the bolts off. And then I tightened them to the manufacturer's specified torque. And I got all his power back. And it's true. What tends to happen is, especially in those days when engines were simpler, my first car, the under the hood looked exactly like my high school textbook. There was a cylinder block, there was a carburetor, there was a starter, there was an alternator, there was a battery, and all the rest was empty space. There were no hoses, there was nothing. There was no feedback. It was like, you know, I was checking the points every month to make sure it would run okay. I was having to adjust things every couple of weeks to keep it in maintenance. That's what people did. Whereas now, I never look under the hood of my car. It's like, you know. So it was a very simple system. And what people worked on their cars, and what people tend to do is they tend to over-tighten things. So when you over-tighten things, like if you over-tighten something, it's got like, if you're sewing and you make the stitches too tight, you get this pucker along the edge. Because you squeeze it and then it's slack, and you squeeze it, it's slack. The same thing happens with your gaskets. So you can't see it, but under pressure, gases leak out, and that's losing power from your engine. So I was just slacking everything off. He retightened it using a torque wrench. And it was like, he said, it was so wonderful. He goes, it's a great car. I said, are you going to tell the other guy? He goes, nah, he can figure it out. So I think somebody else told him in the end, because he improved it. It wasn't the same. So torque is like really useful. It's a bit abstract when you first come across it. It's angular force, if you like. And so what we want is, well, there's my original force. And there's my wrench. So what's the turning effect of that force on that wrench? Well, it depends upon how far away that force is applied, but it also depends upon the direction of the force. If I did this, if I had my wrench like that, and I had my force like that, there's no turning effect. There's none. All I'm doing is I'm trying to pull the wrench away from the bolt. I'm not turning it at all. So the angle is critically important. And so you've got two choices. You can say, I'm going to take the force component that is perpendicular to what we call the lever arm, the wrench. That's one possibility. They've got to be at 90 degrees. Or the other possibility is I take the component of the lever arm, which is perpendicular to the force. But I got to have them at 90 degrees. Whichever I do, I got to have them at 90 degrees. So I could say that my torque is equal to the force times the component of the lever arm, or I could say my torque is equal to the component of the force times my lever arm, whichever you like. But I got to do one or the other. It's not cosine. There's theta. That green component is the sine of theta. It's f sine theta, not f cosine theta. Yeah? So theta is between the direction of my lever arm and the direction of my force. We've seen something similar. We said work was equal to f cosine theta. Oh, so fd cosine theta. And that was, we wanted for maximum work, we wanted F to be parallel to D. And for zero work, we want F to be perpendicular to D. For this, for maximum torque, I want F is perpendicular. I'm calling it R, it could call it D, whatever, you know. And for zero torque, I'd have F parallel to R. So, can you see this is one of those classic cases where these things are similar enough that you can get them confused really easily. So you've got to put them side by side and separate them, make sure I know the difference. There was special math for this FD cosine theta. We said work was equal to the force vector dotted with a displacement vector. Remember that? Yep. Remember that? There's special math associated with this. Torque is equal to the force vector dotted with the R vector. Well, actually, torque is going to equal R dot F. And it's a vector. So when you push on a door, that torque can be visualized as a vector, which points either up or down the hinge depending upon when you push it. If you push it like he did, like the hinge is on this side, so he pushed it like that, then the vector is upwards. And the direction eventually matters, not initially, but eventually matters. I've got an alarm bell going off in my head, just bear with me 1 second. It's going to be, yeah, I think that's okay. I think that's okay, yeah. So we're going to play with it initially, and then later on we'll do the dot product stuff. Okay. So here's an example. Determine the torque of this. So I say, well, my torque is equal to R cross F. I'd like you to just get used to writing that down. And I say I really shouldn't, because it's the magnitude of the torque is equal to RF sine the angle between. I tend to put down the equal sign there, and it really it's a magnitude. This is a magnitude, not a vector. So I should do it as a separate line. I tend to write it all as one line, but I should really write it as a separate line. Okay, and the angle, of course, that angle is there, that phi is there. So we say, well, okay, torque is equal to 3. The r vector goes from the turning axis to where the force is applied, times 7, that's the magnitude of that force, times the sine of 60, which equals, that's going to be something like 21 sine 60. Oh, yeah. So now, what should I be in? Should I be in degrees or radians? Degrees, yeah. It's just we know we've not got any omegas flying around. Yeah, we've just got an angle. So this is going to be 18.2. What are the units for torque going to be? It's going to be N for the force and meters for the displacement. So there we are. So it's not bad. Has my alarm gone off? Did I? Oh, 4 minutes. I got 4 minutes. Okay. So later on, I'll teach you how to do the cross product. It's next chapter. I'll teach you how to do the cross product, okay? For the moment, this is by the by. By the way, if I get the wrong angle, if I make a mistake and I use this angle, so that would be 21 sine 120. I get the same answer. So it's like, I want you to know it's the right angle. I want you to get the correct angle. But by the way, if you make a mistake, you can often get away with it in this little section. Okay, well, okay. So let's use an expression that uses force. F equals ma, good old Newton's law. Here we have a mass. Here we have a force. And that causes an acceleration. Okay. Well, now, here I have a mass, but it's an angular mass, so I call it an I. I'll get to that in a bit. And here I have a torque, and that causes an angular acceleration. So just as I said, the sum of the forces along an axis equals ma. Remember, this was net external forces. I can say the sum of the torques around an axis. This is along an axis. This is around an axis. Is equal to I alpha. Let's do just a quick example with this. A cylinder of radius 3 meters is rotated about its turning axis 0 by a tangential force of 7 newtons. The moment of inertia, I, of the cylinder about the turning axis is 6 kilograms meter squared. Wacky units, and I'll get to that in a little while. What is the angular acceleration about this turning axis? It's very uncomfortable because everything's like new letters and new terms. I was very uncomfortable with the moment of inertia. First of all, the letter wasn't an M, you know. It was I, moment of inertia, I. And inertia is the really, you know, in some ways, it would have been nice if we hadn't called mass, if we'd called it inertia. You know, but we didn't, we called it mass. You know. So just link. Moment of inertia is the angular equivalent of mass. And so I say, oh, well, in this case, then I have torque is equal to I alpha. Let's have a look. My torque is F times D times the sine of the angle between them is equal to I alpha. So 7 times 3 times the sine. Now, this angle between them, it's basically that angle, which is 90 degrees. So that's going to be sine 90. Is equal to 6 times alpha. Sine of 90 is equal to 1. So that's 21 is equal to 6 alpha. So alpha is equal to 21 over 6, which equals 7 over 2, which equals 3.5. And the units are going to be radians per second squared. And I know there's a number of things in there that are a little bit uncomfortable, but you'll get more comfortable with it. The main thing is don't resist them, just overpower them. Just get to the stage where you're going to be overpowering them. The next thing we're going to talk about is moment of inertia. So we're going to spend a little time with moment of inertia. Let's stop there.